Okay, this is the second video for the lecture on September 28, continuation of the discussion on electrode-electrolyte interface, and we came to the point of solving the Poisson's equation for finding the parameters that's related to the material and the junction properties. This Schottky plot is showing that how the capacitance or inverse of the squared capacitance is linearly related to the applied voltage, and the slope of that would present the parameter of the semiconductor electrode interface. So another discussion about the Schottky contact, such a contact that we have a metal semiconductor and we have an energy barrier between them. It's called Schottky contact. It's a rectifying junction. It's behaving like a diode, and for an obvious reason you can see that here is the metal side, on the other side is the semiconductor. So if an electron want to move from the metal to the semiconductor, it's facing a large barrier, whereas the electrons want to go from the semiconductor to the metal are facing shorter barrier. Therefore, because of this difference between the energy barriers, moving electrons from one side to the other is easier than the other, and the device behavior is just more or less non-linear with a rectifying characteristic. As this figure is showing, when we apply some voltage to the semiconductor or across the junction, what's happening is that it's possible to reduce the barrier for electrons from the semiconductor to the metal side, and therefore we can get a much larger current in that situation. Whereas for the case that the voltage to the semiconductor bringing the barrier down, nothing would be different from the metal to semiconductor side, therefore almost no current passes through in the reverse bias. The equation that describes such a system is written up there, and it's like a kind of a diode, a regular diode. We can say that the current is proportional to the exponential of the voltage. And the theory behind that, it's a thermionic emission, and that explains the equation well, and the detail of that can be found in the textbook I mentioned. So, and the ohmic contact was discussed in the class, where we can choose the metal in a way to not generating any barrier between the semiconductor and the metal, and therefore there would be no barrier across the junction. The electrons can move back and forth across the junction, and then the response of the such a junction would be a linear when we look at the current versus voltage. And that's mimic exactly a resistor. So I moved for the second part. I believe that we got to the discussion about how integrating semiconductor and semiconductor theories with the electrochemistry theory. I brought the example that it is more like that when two people from two different countries wanted to have a dialogue together, we need to find a language that works for both of them. So either we need to translate the speak from one person to another one, or vice versa. So it is really depend on that in what field are we discussing. In semiconductor theory, we have learned everything based on energy with respect to the vacuum. So we know the Fermi level, we know the electron affinity, and conduction band, valence band, stuff like that. Whereas in electrochemistry, we usually use a different system for describing the energy in an electrolyte, and that's come from the redox potential. So we know that, for example, the redox potential of the hydrogen is a certain value, and therefore if we wanted to see that what happens at an interface between an electrode and an electrolyte, we need to first kind of match up these numbers. So this diagram is well describing that how we can see both semiconductors and electrochemical potentials in one, in a common ground. So a bunch of the semiconductors that have been used extensively in in electrochemistry have been listed here, so you can read the value of the conduction band and the valence band of them. This axis is versus vacuum. So let's say that if you look at, for example, zinc oxide, it does have about minus 4.3, minus 4.2 electron volt is the energy level of the conduction band, edge of the conduction band versus vacuum. And because it does have such a band gap, so therefore valence band is standing at a very lower level, at a higher energy respect to the vacuum. However, we have been using some sort of different reference, normal hydrogen electrode, for example, as a reference for electrochemical devices, and you can see that if we wanted to match it with the vacuum, there is a sort of the case that for 0 volt of the natural hydrogen electrode, or normal hydrogen electrode, it's equal to minus 4.5 electron volt with respect to vacuum. So practically, if we know what's the electrochemical potential of a reaction from this sort of chart, we can find out that what would be the position of that electrochemical reaction with respect to the bands and the Fermi level in the electrode. So we're going to use that to kind of study junctions between semiconductors and electrolyte. Well, but before getting to the semiconductor part, I would like to kind of bring up this point that if you have a metal electrode, and assuming that metal electrode has the same Fermi level as, or if the metal electrode Fermi level is same as the electrochemical potential of a redox material in an electrolyte, of course, when we insert the electrode into the electrolyte, we do not expect anything would happen because it's already the energy across the junction is the same. But if we have an electrode that we know it's not reacting with electrolyte, and we have a redox system in an electrolyte, and these two do not have the same energy level before making any contact, as soon as we insert the metal into the electrolyte, what's going to happen is that there might be some charge accumulation on the surface of the electrode, and that charge accumulation, according to Poisson's equation, would result in some electric field, and that electric field also generates some potential change. So therefore we may have some potential on the electrode side, and in the bulk of the electrolyte we have a different potential, but because of the accumulated charge at the surface, there's going to be a rapid transition between the unmatched potential between the electrode and electrolyte. This situation, as we know, we call it a double layer charge. So it doesn't need to necessarily we apply any voltage to the electrode to form the double layer. The double layer would automatically form as soon as we insert a conductive electrode inside the electrolyte. Of course, in some applications like supercapacitor, we can even go beyond that and apply some voltage to the electrode to charge the electrode, and therefore getting charge stored in the device. I'm going to stop the video now and start another one shortly after.